This time we're going to consider two simple problems to learn more about scaling and dimensional analysis. 100 cans of paint are required to paint a high statue. We use the same amount of material for a statue to make 1000 smaller statues. The small one is a similar but scaled version of the original one. How many cans of paint are needed to paint these statues? Assume the thickness of the paint layer in both cases is the same. Let's consider the characteristic length of the statue is L. For example, the hand's size. Any part of the body, for example, the size of its head, is proportional to this characteristic length. Then the volume of each statue is proportional to L to the power 3, and its surface, S, is proportional to L to the power 2. We should remind that the amount of cans of paint required to paint each statue is proportional to its area, S. Number of cans are for the smaller statue, the characteristic length is L sub 0, and the highest statue it's L1. Then V1, if we need 100 cans of paint for painting a high statue, the number of can to paint the small statue is 1. And for 1000 statue, it's we need 1000 cans of paint. In fact, increasing L leads to increasing volume and surface, but volume increases as the L to the power 3, but surface increases L to the power 2, and volume increases more rapidly than surface. Now let's consider the second example. In this second example, we consider closed packing. You should have seen the oranges at a fruit shop arranged in an ordered configuration. They are probably closed pack. There are different layers of oranges. Each layer of oranges is on the holes created by lower oranges. Kepler conjectured at 1611 that the maximum packing of similar spheres is pi over 3 square root of 2, which is approximately 74%. This is the ratio of the space occupied by oranges to the total volume, and it's dimensionless. This conjecture remains unsolved until recently. In the last years of 20th century, in fact 1998, T.C. Hales completed the proof of this almost 400 years old conjecture. Now, let's return to our problem. Consider a bowl of peas. We grind the peas. Is the volume of pea flour more or the volume of the original peas? In a bowl of peas, part of the volume of the bowl is occupied by the peas, and some part remains empty. The ratio of the occupied part to the total volume is packing, which we denoted by phi. It's the ratio of two volumes. Then it should be dimensionless. The volume fraction of solid objects, when they are packed randomly, is called random close packing. The relevant parameters are the radius of the P, volume, total volume, and the, which we can construct the dimensionless quantity r v to the power 1 over 3. Then here we have two dimensionless parameters, phi and rv to the power minus 1 over 3. Then packing should be a function of rv to the power minus 1 over 3. As the p's are very smaller volume with respect to the volume of the bowl, and if we use a Taylor's series expansion for the function f and up to first term, the packing is constant, irrespective of the radius of the spheres. Let's approximate the shape of p flower particles by a sphere. Then there is no difference between the volume occupied by the p's and that of p flower. For larger sphere, the space occupied by them and also the space between the spheres are larger. The experimental value of random close packing is approximately 68%. What's the change in close packing, phi, or random close packing if we replace spheres with ellipsoids? We pour a large number of cherry tomatoes into a big bowl. The most effective arrangement of tomatoes is close packed. Then almost 74% of the bowl is occupied. Black plum is almost ellipsoid. If we fill the bowl with black plums in the same arrangement as the cherry tomatoes, which case has more packing, cherry tomatoes or black plum? In the ellipsoid case, instead of one characteristic length r, the radius of sphere, there are three characteristic lengths, say elliptical semi-axis A, B, and C. Then we have four dimensionless quantities: packing, phi, the volume, the total volume to the power 1 over 3 over C, and the equation should be something like this. This equation is almost useless. There are four dimensionless quantities. If we add something else to dimensional analysis, some information comes from symmetries or something like that, we may have more information. In this case, dimensional analysis does not give us much information. But if we turn to the previous problem, into the problem of spheres, any sphere by a linear transformation turn into ellipsoid. By a linear transformation, the problem of cherry tomatoes transforms into the problem of black plums. In this linear transformation, the length in one direction becomes larger while they become smaller in other direction. For example, for a sphere with a unit radius, transform to an ellipsoid with three semi-axes, A equal to alpha, B equal to alpha inverse, and C equal to 1. Then the volume of the sphere is 4 pi over 3, and the volume of the ellipsoid is, which is the same. Then the volume of each ellipsoid is the same as that of original sphere. This transformation does not change the total volume and the number of ellipsoids. So unoccupied regions and packing also remain unchanged. So if we arrange the ellipsoid with the same arrangements of the close packed spheres, the packing has the same value, 74%. Obviously, in this arrangement, the semi-axis of all the ellipsoids are parallel. Consider this figure. A group at Princeton University was surprised to find the maximum random close packing for ellipsoids for A equal to 1.5 approximately is almost 73.5. This amount is much more than random close packing, 68%, and is roughly equal to close packing, 74% for spheres. The meaning of these strange results could be that perhaps ellipsoids can be arranged in some other configuration so that the packing is more than 74%. This group reached to the number of 77% with a special configuration. In this configuration, the ellipsoids in one layer, for example, are in this shape, and in the other layer, they are not. Their axes are not parallel to the lower layer. They are, for example, in this shape.